Uh, Hello, my name is Min-Soo Kang, and I'm graduate student at Hanyang University in Korea. My advisor is Professor Simon Song, and today I'm going to talk about numerical analysis of electric heat sources in a Hyperloop system to develop a cooling system. Hyperloop is the future of high-speed transportation. It utilized electromagnetic pulse to levitate and propel transport capsule within low-pressure tubes, reducing air resistance and friction. This enables the capsule to accelerate to subsonic speed. To create levitation and propulsion forces, current is applied to the propulsion and levitation coils, leading to heat generation due to ohming losses. The propulsion coil is the primary heat source, and to ensure normal operation, its temperature must be kept below 333 Kelvin. To achieve this, a comprehensive analysis of system thermal validity becomes essential, and a well-designed cooling system is imperative to regulate the temperature effectively. There are thermal challenges within the Hyperloop system. The first, this section shows the guideway and concrete tube with propulsion and levitation coil encased in epoxy molding. The low thermal conductivity of epoxy and concrete, along with insufficient air for convective cooling inside the tube, hinders efficient heat transfer from the propulsion coil, resulting in heat accumulation. Second, the initial flow speed of the capsule leads to longer duration within each acceleration section, causing an increased time per current application. As a result, this section experiences higher heat generation compared to others, leading to an imbalance of thermal load between sections. To address these issues, we have devised an effective cooling system. To address uh, the problem mentioned before, our research aims to design a hybrid cooling system that combines passive and active cooling method for the Hyperloop. By evaluating performance of both approaches with different design parameters, we seek to enhance the system's cooling efficiency and performance. Uh, we have conceptualized a hybrid approach utilizing both active and passive cooling methods. For the Hyperloop system, the active cooling method proves suitable for acceleration and deceleration sections where thermal loads are high and section length is short. The passive cooling method is applied in opposite situation. Our design incorporates both active and passive cooling methods tailored to the unique demand of each section. Our passive cooling system utilizes a closed-loop thermosiphon comprising an evaporator and a condenser. In light figure, blue region is water and vapor channel, and green region is propulsion coil, and purple region is epoxy. The thermosiphon effectively extracts heat from the coil and channeling it to the condenser and dissipate it, positioned outside the tube. In our study, we focused on two critical design parameters for the thermosiphon system: the internal pressure in thermosiphon and the condenser's heat transfer area. We conducted investigation across three distinct cases to enhance performance. Uh, System pressure of case 1 is 0.2 atm and case 2 is 0.1 atm. System pressure of case 3 is 0.2 atm with an increased cooling area by pinned condenser. In our analysis, we consider the properties of water and steam at varying pressure, utilizing the values listed in the table. For the flow channel material, we tested alumina for its low electrical conductivity and high thermal conductivity. Our simulation employed the volume of fluid model for multi-phase analysis, coupled with the Bob boiling model for phase change consideration. And we applied an insulation condition to the epoxy surface. Additionally, the condenser experienced an ambient temperature of 313 Kelvin, featuring a heat transfer coefficient of 10. For the filling ratio, we initialized it as 50%. And for the coil's heat generation, we defined the propulsion coil's current time as per second, and steady-state simulation was conducted. We compared the cooling performance per each case. In case 1, an active phase change occurs in the lower region of the propulsion coil, resulting in a significant cooling effect in that area. In case 2, the condenser's small temperature difference between saturation and ambient disrupts the phase change process, leading to vapor accumulation in the evaporator and preventing efficient circulation cooling. Case 3 shows superior cooling efficiency than case 1. An active phase change occurs in the upper region of the propulsion coil, producing substantial cooling effect in that area. Among the cases, case 2 shows a maximum temperature below the temperature limit, but it lacks phase change in the evaporator. Only case 3 successfully achieves circulating cooling through phase change and effectively cooling the system below the target temperature. Our active cooling method employs a vacuum pump installed at regular interval to maintain low pressure within the tube. To efficiently cool the coil, we devised the cooling passage distinct from the tube's interior to avoid any interference with the vacuum system. The cooling passage is located at the layer of the coil structure, and during cooling operation, the vacuum pump generates a flow that efficiently pulls in ambient air. We consider the installation interval of vacuum pump and the cooling passage shape as crucial design parameters. The cooling passage is positioned layer of the propulsion coil, facilitating convective cooling of the coil's layer section through fluid flow. To save computational cost, we consider the highlighted region and a periodic shape that covers one propulsion coil. Two distinct cooling passage shapes were investigated. First one is the rectangular shape, which cools only one side of the coil, and second one is the extended shape, which is capable of cooling both the upper and lower side of the coil simultaneously. We conducted a steady-state simulation and we applied adiabatic condition to the epoxy surface. For the current time, we used the average value during the acceleration phase, and the physical properties used in the analysis are detailed in table. And we explored 6 different cases of vacuum pump interval, ranging from 700 meters to 4,200 meters. Per each case, we calculate the mass flow rate, considering the vacuum pump curve and ideal gas law, and utilize them as initial value for periodic boundary condition. Displayed here is the temperature distribution for case with a pump interval of 700 meters. In the extended flow path, the fluid flow passes over the top surface of the coil, resulting in additional cooling effect compared to the rectangular flow path. When comparing the maximum propulsion coil temperature, both the rectangular and extended flow paths successfully achieve coil cooling below the target temperature per hour interval. As demonstrated by the temperature distribution, the extended flow path shows a reduction up to 4 Kelvin in a maximum temperature compared to the rectangular flow path. Additionally, the pressure drop within the flow path decreases by approximately 23% in the extended flow path compared to the rectangular flow path due to extension of the flow path. Therefore, the extended flow path enhances cooling efficiency and reduces pressure drop in comparison to the rectangular flow path. And this allows for wider pump interval in the design, potentially reducing the required number of vacuum pumps and resulting in cost saving. In summary of the entire presentation, first, we proposed a passive cooling method utilizing a closed-loop thermosiphon and compared the cooling performance based on the system pressure and the heat transfer area of the condenser. And second, the passive cooling method enables circulation cooling with phase change and achieves adequate cooling performance to cool the coil below the temperature limit when the system pressure is 0.2 atm with a pinned condenser. Third, we introduced an active cooling method utilizing a vacuum pump and compared the cooling and pressure drop performance based on the pump interval and flow path design. And first, by utilizing the extended flow path, we enhance the cooling effect and reduce pressure drop compared to the rectangular flow path. And this allows for a wider pump interval in the design, potentially leading to cost savings. And thank you for listening.